So everything all set.
Yeah. Now, hand over to Dr. Mohan. You are the moderator for today's session proceedings. Floor is to you. Please.
Okay,
good morning, esteemed speakers, distinguished guests, and participants. It is a privilege to welcome you all to the valedictory function of the 20-week Radar Meteorology Lecture Series, a collaborative initiative by South Asian Meteorological Association, SAMA, and ACARR, CUSAT. This program has illuminated as the forefront of radar meteorology, fostering collaboration and innovation. Without further delay, let us commence today's proceedings. Now, it is my pleasure to invite Professor Dr. Someshwar Das, sir, Secretary General of South Asian Meteorological Association, SAMA, to deliver the welcome address. Dr. Someshwar Das, with his visionary leadership, has been a guiding force behind this initiative. Sir, the floor is yours.
Thank you very much, Dr. Mohan. I hope I am audible clearly.
Yes, sir. Yes.
Right, sir.
Great, thank you. ABM Dr. Ajit Tyagi, Saab, President of SAMA, the Chief Guest, Professor Dr. M. Junaid Busiri, Vice Chancellor of the Cochin University of Science and Technology, the Guest of Honor, Dr. G. Viswanathan, former Director, ISRO, ISTRAC, distinguished speakers, Dr. J. Vivekanandan, NSF, National Center for Atmospheric Research, USA, and Dr. Anita Daniel, Deputy Director, ISRO, ISTRAC, Dr. Devendra Pradhan, Chairman Advisory Panel of the Lecture Series and former EDG of IMD, Coordinator of the Lecture Series, Dr. S. Avilas, Director ACARR, CUSAT, esteemed members of the Executive Council and Advisory Panel of SAMA, members of the Organizing Committee, distinguished participants from member countries of South Asia and non-aligned movement, ladies and gentlemen, a very good morning from Nepal. We welcome you on behalf of the South Asian Meteorological Association, SAMA, and Advanced Center for Atmospheric Radar Research, ACARR, of Cochin University of Science and Technology in India. We are delighted to inform you that the 20 weeks lecture series on radar meteorology held during 25 May to 16th of November 2024 has been successfully completed jointly with Advanced Center for Atmospheric Radar Research of Cochin University of Science and Technology and the SAMA. This is a continuation of our efforts on capacity building of the people of South Asia and the member countries of non-aligned movement, NAM. Many of you may know that we conducted the first online lecture series on atmospheric physics jointly with the SRM, Institute of Science and Technology at Chennai for 4 months during January to April 2023, in which more than 2,000 people from 48 countries registered for the course. We conducted the second online training on the WRF modeling system jointly with CDAC, that is the Center for Development of Advanced Computing, India, for 3 weeks during 3rd to 24th April 2023. With hands-on training on the supercomputing system of CDAC, we conducted the third lecture series on satellite meteorology for 20 weeks during September 23 to February 2024. And this is our fourth course on radar meteorology for the capacity building of the people of the member countries of SAMA and institutional member countries of NAM, RIMES, and ICIMOD. We had a distinguished panel of very senior scientists and professors from reputed institutions of this region who are experts in the field. The syllabus of the lecture series was designed based on the feedback and requirements of the member countries of SAMA. The lecture series was targeted at postgraduate students and professionals of non-meteorological backgrounds who are interested in learning the subject of radar meteorology. About 1,200 candidates from 48 countries registered for the course. A majority of them attended the live lectures, while some of them attended the lectures archived on YouTube channel of SAMA due to the time difference between India and other countries. Detailed statistics about the actual number of participants, their attendance record, their grade scores, obtained in the final exam, and summary of the feedback will be presented shortly by Dr. Avilas, who is also the coordinator of the lecture series on radar meteorology. Grade certificates like outstanding, excellent, very good, good, etc. will be given to the participants based on their scores in the final exam. Appreciation certificates will be given to the participants who have attended at least 75% of the lectures, while the participation certificate will be given to the rest of the candidates. All lectures were live streamed and archived on the YouTube channel of SAMA. They are being viewed by many people even after the lectures are over. The attendees had good interactions with the speakers in the question and answer session. We feel satisfied that the entire course, including all the previous lecture series, were conducted free of cost for the capacity building of the people. For those who are not familiar with the background of SAMA, let me just briefly tell you that the South Asian Meteorological Association, SAMA, is an association of 9 South Asian countries, including Afghanistan, Bangladesh, Bhutan, India, Maldives, Myanmar, and Nepal, and Pakistan, and Sri Lanka. It is a professional, non-profit international scientific society having headquarters in India for the promotion of meteorological and allied sciences and their applications for the safety, well-being, and sustainable development of the citizens of the South Asian countries. Established on 3rd August 2020, it has about 700 members, including professionals and students from the 9 South Asian countries, which are increasing day by day. SAMA organizes webinars, training workshops, capacity building programs, special day celebrations like the WMO Day, Ozone Day, quiz contest for school children, special lectures on the works of the Nobel laureates, etc. We are happy to inform you that presently SAMA is organizing the first Olympiad in meteorology, weather and climate sciences for the school children of class 8 to 11, coinciding with the celebration of the 150 years of establishment of India Meteorological Department. So thank you very much for your kind attention and have a nice day. Over.
Thank you, Professor Dr. Someshwar sir, for your enlightening and inspiring words, who is setting the tone for this auspicious event. Next, we have the honor to hearing from the Air Vice Marshal retired Professor Dr. Ojit Tyagi sir, who is the President of South Asian Meteorological Association, and his exemplary leadership has been pivotal in advancing the meteorological community across South Asia. Sir, please proceed.
Thank you, Mohan, and very good morning, namaskaram, and I extend heartiest welcome to our guest of honor, Dr. Viswanathan Sahab, keynote speakers, Vivekanandan, Dr. Vivekanandan, Dr. Srimati Anita, Daniel, Chairman of our advisory committee, Dr. Pradhan, members of the organizing committee led by Dr. Abhilash. At the outset, let me acknowledge and thank CUSAT. I am sorry that Honorable Vice Chancellor is not able to join us because of some urgent commitment in the university, but I'd like Abhilash to convey our gratitude to the CUSAT and the support extended by the Advanced Center for Atmospheric Radar Research in organizing this 20 lecture series very, very efficiently. Appreciation to Abhilash and his team of Shrikala, Rakesh, and other who on all Saturdays were available to conduct this online series very, very efficiently. We are also thankful to all our eminent speakers who really provided the first-hand deep knowledge of this radar meteorology and their application in research and the operations. So this was not only theoretical course program, it was devised in such a way that people start applying the radar products in operations and also use the data which is being made available by IMED for the research. We also introduced lectures from the industry. So the industry participation in development of radar in South Asia is very vital. And so that was the great thing. Our inaugural session was graced by Dr. Chandrasekhar from Colorado State University and Dr. Mohan Kumar, the founding director of ACARR. And also now we have in our valedictory function two eminent radar meteorologists, Dr. Viswanathan and Dr. Vivekanandan. So thank you very much. I know Viswanathan Sahab has got very busy schedule and family commitments, but he has agreed to give introductory talk on the indigenous development, of which he has been, I think, a very, very important pillar in the country. Once again, Somesh has covered the activities of SAMA and capacity building. This wouldn't have been possible without the support of all our eminent meteorologists in the field of radar from IMD, ISRO, academic institutions, and industry. So it's a partnership, and I'm very happy that we are able to bring the state-of-art knowledge about the radar meteorology to the students and the young researchers from South Asia and the named countries. So once again, welcome. Thank you so much for joining. And again, my gratitude to the CUSAT for organizing this particular important 20 lecture series on radar meteorology with SAMA. Thank you. Jai Hind.
Thank you so much, Air Vice Marshal Professor Dr. Ajit Tyagi sir, for your insightful remarks and for your unwavering dedication to the cause of atmospheric sciences. It is now my privilege to introduce Dr. Abhilash as Director of ACARR and Program Coordinator of this lecture series. His tireless efforts and strategic vision have been cornerstone of this program. Dr. Abhilash, the stage is yours.
Yeah, thank you. Thank you very much, Dr. Mohan. Good morning to all. Good morning, Professor Tyagi Saab, Professor Somesh sir, today's guest of honor, GV sir, and today's distinguished speakers, Vivekanandan sir and Dr. Anita madam, and our advisory panel member, Chairman, Dr. Devendra Pradhan sir, and Professor Chandra, and all other distinguished panelists and participants. Very good morning to the valedictory function of this 20 lecture series in radar meteorology. I have made a slide for 5 minutes. We will go through it and we'll present a brief report of the activities in 5 minutes. Let me share my screen. Thank you. Actually, there were almost 1,189 registered participants from 47 countries and spread across different domains, like from
Sir, move the slide. Sir, slide is not moving.
Okay, now it is okay, right, Swagata?
Yeah, it is okay now.
Yeah. So there were 1,189 registered participants spread across 47 countries. And if you look at the highest qualification-wise, most of the PhD students, MTech, BSc, MSc students, they were sharing the most. And then age-wise, that is very important. So age-wise, maximum participants were from 30 to 45 years, middle age or the early career scientist, and students participations like 29% from 15 to 30 years, and there were almost like 90% of participants were above 21% from above 60 years. So that itself demonstrate the wide ranges of participants across different countries, and they have interested in this course. And also most of the participants, as this is as part of the SAMA's capacity building in South Asia, so most of the participants were from South Asian countries. So yeah, this we have inaugurated this with the Dr. S. Raghavan Memorial Lecture delivered by Professor Chandra. And there were many lectures like Pradhan sir and Kannan, Gajendra sir, Reddy sir, and then Suresh sir, Thambi sir, T.N. Rao sir. And we have conducted a midterm exam, then Dr. Pandi, and followed by Somasan and Dr. Amarjodi, Dr. Anand Kumar Das, Dr. Ashish, and uh, myself. And then it is ended with Dr. Mohan Kumar Das presentation. So, and followed by there was a industrial presentation from Astra, and also Gajendra Kumar sir presented the IMD's future plan in radar network. So this was conducted, and followed by that we have conducted an online test, and based on the test and the score scored by the participants, we have given different type of grading and certificate to each of the participants. And this is the total distribution of the points scored by most of the participants scored between 45 and 50 out of 60. So that itself is showing the interest among the participants, and they were attending the course very, very seriously. And based on the participation and based on this course, we are issuing different certificates with their scores in the certificate. And this is the country-wise participation for the all course. I must say that maximum participation was for the Devendra Pradhan sir's, our advisory panel chairman. Devendra Pradhan sir's lecture received maximum participation, and also even in the YouTube channel also maximum hit is received by Devendra Pradhan sir. So that itself showing his nice presentations in this course. And there were good email response we have received, and also we have distributed the feedback forms that also we received, and there are some few suggestions as well. So for the improvement, that is also I must share here. So, and then these are some of the feedback. So more than 60% of the participants were very much happy about, and maybe if you consider together 4 and 5, it's response is very good. And these are the, and this exceptional radar meteorology course is a success because of the three eminent personalities for their exceptional leadership and mentorship. So that is none other than Professor Tyagi sir, Somesh sir, and Devendra Pradhan sir. They were guiding us to conduct this program in an efficient way. Every time they were interfering, and they are giving guidance to conduct this program. And also the success is also attributed to the collaborative effort, including the advisory panel members like Devendra Pradhan sir, T.N. Rao sir, Pandi sir, Rajesh, Dr. Ashish, Dr. Gajendra Kumar, Dr. Jayandipal, Dr. Shal, and Dr. Tan Nang, and Dr. Govinda, and also the organizing committee members, including Srigala, Ragesh. So the support from the organizing committee members, including the national executive members like Dr. Sagada. I must explicitly tell their names: Dr. Sagada, Dr. Lakshmi, Dr. Divya, Dr. Lohini, Dr. Mili, Dr. Mohan Kumar Das, Dr. Fatima, Dr. Madan Sigdal, and Dr. Paulami. They were very much helpful in conducting all these proceedings throughout this 2021 lecture series. So we are very grateful to all of them for conducting this in an efficient way. Actually, this is a team effort. When we talk about the people behind the screen, not behind the screen, they are in front of the screen to conduct this efficient lecture series. I extend my heartfelt gratitude to advisory panel, the local organizing team for their unwavering dedication and hard work. Their attention to detail and innovative solutions were pivotal in overcoming challenges and ensuring success of this activity. The collaborative effort of everyone involved was instrumental in achieving this outstanding outcome, especially Mr. Ragesh, Dr. Srigala, Mr. Rijoy, Mr. Sharath, Mr. Abhiram, and Mrs. Sunida. The help received from them is immense, and they were actually behind in front of the screen to conduct this program in an efficient way. So finally, one minute. This activity, just 1 minute. So this is the activities to summarize. That is it. Over to you, Dr. Mohan.
Thank you. Thank you, Dr. Abhilaji, for your thoughtful reflections and for your invaluable contribution to this initiative. By this time, all of you may knew that there is a strategy happened in the university. 2 students lost life in the Charai beach while taking the bath, and 1 student is from CUSAT itself. So we deeply mourn the loss of the students. Our thoughts and prayers are with their family and their loved ones. Rest in peace, both of them. Due to this, our honorable guest, chief guest, is not able to join this program. Sir is very Professor Bushi sir is very busy there. Now, I have the privilege to welcoming Dr. Davendra Pradhan sir, who is the chairman of the advisory panel, to deliver his address. Dr. Pradhan's expertise and strategic insight have significantly shaped the success of this lecture series. Dr. Pradhan sir, the floor is yours.
Good morning, everyone who is present for this valedictory session today. I am feeling a lot of pleasure here, and my insight, happiness, and I'm unable to show everything that how could I express the things when I'm looking for Professor Chandrasekhar, who is our not only the eminent scientist, but a mentor and a guide who has guided us to the many miles ahead where the India was working with the lot many things available with the old systems, and then gradually modified day by day from Doppler radar to single pole to dual pole and others. So I have got this high gratitudes for Professor V. Chandrasekhar, who has given a lot of support and guidance. Professor Ajit Tyagi sir, who has taken a lot of efforts in the development of the SAMA, and Professor Someshwar Das ji, who has also taken a lot of efforts for everything in the development of this this non-profitable organization, a highly technical organization who has conducted many lecture series. And today, once again, I am grateful to Professor G. Viswanathan sir. I am known to him, and I have learned many things, Professor, from Professor Viswanathan sir. When I was working in India Med department, I could meet him many a times in the ISTRAC, and personally, I discussed many things. So many of the things I learned from Professor Chandrasekhar, Professor Viswanathan sir, and under the leadership of Professor Tyagi sir, when he was our DG, we could manage many things in the IMD. Professor Vivekanandan sir, who has written so many books and who is doing a lot of research in the Doppler weather radar, and I have read his so many books, and still I have got some books with me written by Professor Vivekanandan sir, Professor Chandrasekhar sir, and others here. So it's a high privilege for every one of us to see all these eminent scientists here, and I welcome. And once that Professor Vilash told me that my lecture was this thing having the maximum hits on the YouTube, so I felt that I could do something for this lecture series. I don't know how far it was possible for me, but some of the members from the different countries like Nepal and others, they wrote to me. They wanted to have a designing of the radar training course and others here, because when they saw many things that how we have conducted very successfully under the leadership of Professor Abhilash, I should say that his team has played a very important role. So many scientists from the different countries, they were very much impressed with the contents, with the lectures delivered by many of the eminent scientists, and especially Dr. T. Narayan Rao, uh, Dr. Gajendra Kumar from IMD, and so many scientists from IMD is presented their lectures. So as a part of this training session, I feel obliged, and I am very happy that everyone has contributed very nicely. And the guests, those who have joined today, Professor Viswanathan sir, Professor Chandrasekhar sir, Professor Vivekanandan sir, and others, I will remain grateful to you, sir, because without your blessings and without your presence, this could not have been possible. Professor Someshwar sir, I have got this. Really, I cannot express in word that how much you have contributed in the development of the Sama, Professor Tyagi sir. So just I stop myself here, and once again with many thanks to every one of you who has joined today, sir. I'll remain grateful to you, sir, for everyone. Thank you very much.
Thank you, Dr. Davendra Pradhan sir, for your enlightening words and for your invaluable guidance throughout this journey. Thank you, sir. So there is a little changes regarding the lectures. The Abhilash first lecture will be given by the Vivekananda sir, right? You're muted.
Yes, by seeing their face, yes.
Okay, yeah, I understand. It is now time to introduce our first distinguished speaker, Dr. Vivekananda sir, a leading scientist at the National Science Foundation, ANCAR and UCAR, renowned for his groundbreaking work in radar meteorology. Dr. Vivekananda sir will present a lecture on advancement in radar meteorology. I would like to invite Dr. Rohini L. Bhawar from SP Pune University to formally introduce our honorable sir. Dr. Bhawar, please proceed.
Thank you, Dr. Mohan. Yeah, thank you, Dr. Mohan. So, good morning, all, and a short introduction. Dr. Jyotiram Vivekanandan, also known as Vivek, is a senior scientist at the Earth Observing Laboratory, ANCARR, Boulder, Colorado, USA. His research and development work includes polarimetric radar, dual wavelength radar, phase array radar, LiDAR, and microwave radiometers. He is a fellow of the American Meteorological Society and an associate editor for Radio Science. The 2018 European Geophysical Union's Christian Huygens Medal was awarded to Dr. Vivekanandan for his pioneering and groundbreaking work on the microphysical characterization of clouds and precipitation using advanced remote sensors. Prime examples of his leadership are his development of a dual wavelength radar system created by adding a millimeter wave radar to the ANCARR's S-band polarization radar, that is S-pole, and his scientific and technical leadership to the development of an NSF-funded cloud radar for Gulfstream V research aircraft. He led the composition of the NSF MSRI-2 airborne phase array radar, that is ACARR, proposal project description, working closely with the ACARR team. The project description team made a clear and compelling case for the need for ACARR. NSF funded the $90 million ACARR project. It is a transformative technology for weather remote sensing with several novel ideas and concepts. So welcome, sir, and over to you, Dr. Mohan.
Thank you, Rohini. Now floor is open for Dr. Jyotiram Vivekanandan, sir, please.
Okay. See, let me share my screen. Is that screen is visible? Is that
Yes, sir. Perfect.
okay? Thank you very much. Thank you for the kind introduction, and thanks to Professor Tyagi and GV inviting me on behalf of SAMA for presenting this lecture today. Today, my lecture has three sections. I thought it's more like a popular lecture, and so I'd like to go a little bit about basics about the radar, kind of give a good introduction to radar. Then the second part introduce how you could detect in situ measurements, what you can do with that, with the radar. Now, how do you combine the in situ and the remote measurements like that? It applies to about drizzle onset in a cloud. The third part will involve about rain maps. So it'll have three parts to it. Let me start with the first one here. Given that this lecture basically also, it kind of honors Raghavan Sahab. I thought, he has a lot of interest in, not interest, he has done the books on radar meteorology, a lot of applications. That in this honor, I thought I'd do some radar signals here, the first part. The radar signal, basically, if you look at it, comes from a clouds, contains a lot of raindrops. In this case, let's say, typically raindrops are between 1 to 5 millimeter, 10 centimeter apart. So weather radar transmits 1 megawatt power, about 10 power 6 watts, but very sensitive radar. It's about minus 100 dBm, about 10 power minus 13 watts. Hence the receive power is large, but it's very sensitive radar. Compared to the cell phone signals, it's about minus 90 dBm, about 10 times. The radar, whether it's more sensitive than a cell phone signal, and cell phone towers could interfere with the radar measurements. And the weather radar is quite sensitive in that case. It transmits a lot of power. At the same time, it can detect very small signals. The radar is a block diagram, simple one it shows here. It's we have a reference frequency on the leftmost extreme. It's a GPS 10 megahertz. With that, we have two channels, basically are two oscillators. The Stalo, which is about, in the case of a S-band, it's about 3 gigahertz. Then Coho is a coherent local oscillator, which is about 60 megahertz for IF. With that, we transmit a signal, basically a sum of 3 gigahertz with 60 megahertz. Then the bottom diagram shows signal returned with a Doppler shift with those two frequencies combined. Then we mix with the Stalo, which is 3 gigahertz, down convert to about IF frequency, amplify it. Then we generate basically the I and Q in the baseband. The I and Q is the basis of any radar processing. And so if you want to have a master of how the radar functions, what you can do with that, we have to know I and Q in the engineering level. In I and Q, how they look like this? It shows 4 different panels. The channel 1, channel 2, so about 64 time steps. This I is a column 1, column 2 is a Q. These are the signals for various Doppler velocities or spectrum width. You can see how it basically varies as a function of time. The I and Q basically used to generate all the products in the radar, like a DBZ, reflectivity, Doppler velocity, and spectrum width. Now, I and Q, how do they look like that? The top channel looks basically ensemble of I and Q time series, which basically is zero mean, and you see about 64 time steps, as you say it. The I and Q both are zero mean, basically. And so basically zero mean Gaussian process. And so this is a property of the I and Q signal, what we receive at the radar from the clouds. If you look at one I and Q signal here, what I show is a time domain, which is about 64 milliseconds, as you say it. The top one is the I channel, bottom is the Q channel. There are 2 different channels. Then the bottommost panel shows basically the Fourier transform of what we see in the top 2 panels. In this case, the I and the Q are shown for 20 meters per second with 1 meter second spectrum width. You could see the 400, the Doppler frequency for a S-band, basically that amounts to 20 meters per second wind, the Doppler wind, with the some spectrum width that corresponds to the 1 meter per second. This is how you process the data. You receive the INQ, then you can do the pulse pair processing, or we can do a basic Fourier spectrum, look at the signal. And this is a very basic way how you look at the radar. The same thing applies to either profiler, any radar, the same concept applies. Hence, do you want to master about the radar signal processing, you should have a very good understanding about the I and Q, which are the basis of the radar signals, the time domain, frequency domain representations. So once you understand that part, then comes how accurately you can measure the wind measurement. In this case, what I show is on the x-axis number of samples, on the y-axis the spectrum width, for a signal noise ratio about 0 dB in this case. How many samples you need? Because these are random signals. We need to average a number of signals to get a reasonably a good estimate of wind. In this case, it's not a dB on the right side, it's a meters per second. Then if you look at it, in this case, let's say for a 0 dB SNR, even with about 100 samples or 80 samples, still your error will be more than 1 meter per second. If you go to a 10 dB or 20 dB SNR, that means it's 100 times signal is larger than the noise. Then you could look at, you don't need that many samples. The less number of samples, you can get a better estimate of the wind measurement. If you go to 30 dB, in this case, 1,000 times stronger signal than a noise, then look at, that's a big difference between 20 and 30 dB. Once you got about 20 dB signal, you got a very good estimate of wind measurement with most of the samples. And so this is the basis of how you decide how many samples you want to collect to estimate a radar observation, in this case, a wind. If you look at a DBZ measurement, the spectrum width, again, the y-axis, the exact number of samples, then there's a certain difference between previous velocity estimate and the power estimate. The previous thing, look at this, compared to this figure is kind of inverted. The reason being, for estimating velocity, you need a coherent signal. But estimating a power, we need a more like incoherent, more like independent measurements. That's why signals, these plots are kind of reversed one to other. Then you got a smaller spectrum, larger spectrum width, small number of samples are good enough to derive reflectivity, SP reflectivity, 0 dB SNR. You go to larger SNR, you get a much higher, better way of characterizing the reflectivity, the lower standard errors. If you go to even 30 dB SNR, you can look at it even about 60 or 40 samples, you can get a very good estimate of DBZ measurements. And this is the first part of my lecture here, basically shows how the signals are used from the basis of I and Q, knowing those characteristics in time domain, then we can estimate how accurate you can estimate velocity and the power estimates. So that's the basis of a Doppler radar. In polarimetric radar, extension of Doppler radar, there are two polarization. But once you understand Doppler radar, it's much easier to understand all the digital electronics in polarization radar. Now I move on to my next topic. This is subsections about drizzle onset. The drizzle onset, what it means here is, see, you got a cloud. The cloud doesn't rain. It's just cloud droplets, less than 50 micron. But it has to grow to big enough to become a raindrop. Not every cloud produces a rain. There are ways you can detect this. We have a airborne platform with the cloud probe, precip probes and airborne platform or the airplane. We can sample them. We can see which clouds are going to be raining, which cloud is not going to rain. But how do you do that? Using a remote measurement like a LiDAR measurement. That is that basically a description going to be given in this subsection here. I'll be basically discussing about, in this case, about stratocumulus cloud. Stratocumulus cloud look like this. They are less than 100 meter or 150 meter deep, very thin, but they're very widespread. These clouds are very widespread over the oceans, over the land, can exist for minutes. These are stratocumulus cloud. After some time, become a raining cloud. How it becomes raining cloud is the long process, but that's how it happens. Now, if you look at statistically, the stratocumulus cloud covers 23% over the ocean, 12% over the land. And this is a very extent coverage of a cloud system compared to thunderstorms or other clouds like that. Then liquid cloud could be determined by droplet size. Once the droplet size, liquid water content could be estimated. It's quite important for Earth radiation budget. And so understanding stratocumulus cloud is quite important in the case of climatology or climate or weather from cloud to rain processing. So cloud depths are quite shallow. These clouds are very small cloud droplets. We got to able to detect them using cloud radars. It's possible to do that. Then how do we do that? This graph shows on the y-axis a size. On the x-axis, the ratio of two measurements. One of them is reflectivity from the radar. The beta is from LiDAR. The ratio between two power measurements raised to the power 0.25 plotted as a RLED. We define a size just using remote measurements, because in the case of in situ measurements, they basically in situ measurement, they have a MVDs, medium volume diameter or D effective. These sizes cannot be estimated from remote measurements. It's only for in situ. For remote measurements, having a reflectivity or LiDAR, we cannot do with that. Hence, we define a sizes based on remote measurement alone. Like what you see here is RLED in micrometers. That is how we defined it. It's a linear relationship. That's all to it. Once we can do this, then we can detect whether cloud does it rain or does it just a cloud droplets. Now, in this figure, on the x-axis, what I show is a standard deviation of droplet spectra that is measured by in situ probes. Plotted in terms of x-axis is the radar, LiDAR estimated size. What I show is the in situ measurements. The green color shows drizzle droplets. The blue color shows cloud droplets. The yellow color shows the transition from the cloud to drizzle droplets. This is using in situ measurements. It's if you look at this curve, the yellow where transition happens between about 25 micron up to 150 micron. That's the transition zone between cloud to drizzle. A lot of work goes into this because one of the fundamental research in cloud microphysics is to understand how the cloud become a drizzle or rain, what makes it. And so this is using in situ measurement. I show the regions in the yellow where the drizzle and basically cloud to rain transition happens. If you look at the remote measurement, this is basically using the radar and LiDAR measurements. I use them in a fuzzy logic scheme. The altitude is shown on the x-axis, and on the y-axis altitude shown. It's about less than 2.5 kilometer cloud top in this case. And x-axis the time is about, in this case, this is basically about 5 minutes of data from an airborne platform, about 42 kilometer in the distance on the x-axis. I show the 4 different classes here. The cloud is shown the blue color. Cloud to drizzle, where the cloud becoming a drizzle, shown the yellow color. The drizzle is a green, red is a rain. If you look at it, the cloud become drizzle, the yellow, then the green, the drizzle droplets, then the rain. And so logically it fits what I show here. Could you verify this? Unless someone flies into the clouds, it's difficult to do all the verification in coordination with the radar measurements. It's not that easy to do it. But logically, what I show here shows the transition from cloud to rain. And that's what's shown using the remote measurements. Now, is it possible to correlate the yellow color, what I show here, because I could estimate the size using remote observations, do a histogram. This is from the remote measurements. The blue is a cloud. Yellow corresponds to where the transition takes place. That's about 25 micron to 150 microns here. Then below that, I repeated the same thing with the cloud or drizzle to drizzle like that. Hence, yellow color, what it shows on the RLED, the size estimated from the remote measurement, corresponds to the yellow color shown in the in situ probes. This is quite interesting because this measurement, what I show in yellow color, is in situ probes, which is about from the cloud or drizzle probe flown into the cloud using an airborne platform. The same in situ probe measurements of cloud drizzle transition corresponds to the yellow color here, the yellow show here. This is from remote measurements. And so this series of plot shows how you could use radar or LiDAR measurements to detect the onset of drizzle. That means how the cloud could become a rain cloud. And so this is basically a microphysical study using in situ and the radar measurements, where we're able to show in situ measurements sampling volumes are just in meter cube. The cloud sampling volumes, the remote measurements, the LiDAR is about hundreds of meters. How do we relate this huge sampling volume to small sampling volume? Based on the things what I show here is possible in certain situation in a stratiform cloud. The picture what I show in the histogram came from remote measurements. Picture what I show here is in situ measurements. The yellow boundary on the x-axis, if you look at it with 25 micron to 150 micron, that corresponds to the yellow regions in this measurement, which is remotely detected using radar and LiDAR measurements, corresponds to the sizes. And so there is a link between cloud to drizzle could be detected once you have the right set of measurements in stratiform clouds. This is my basically a second part, which kind of showed the link between in situ and the radar measurements. The third part is the most important part. Cloud microphysics is important, but even more important is rain maps. Rain maps are the end product. I mean, what kind of rainfall rate every day or every 10 minutes or every month, every season. This is a key product all the radars will produce at some point. Now, in India, there's a historical background. There's a major drought in 1877. IMD established a huge network of rain gauge. Between 1951 to 2003, IMD basically had about 6,000 rain gauges with the various people, various agencies, 500 from IMD, 520 from Hydromet department, then agro stations, then other state governments. A lot of rain gauges in India. So out of which, even though 6,000 rain gauge existed, only 2,000 really gave a good measurements 90% of the time, the 50-year period. Rajivan and their group published a fantastic paper. These are the rain gauges located about 2,000 rain gauges which they used in analysis. They produced a landmark paper where they did gridded. It's about 100-kilometer gridding. What they did 1 degree by 1 degree or half a degree. They did some of the products like that. they compared how the rainfall statistics. It's a daily rainfall, they did that, seasonal rainfall, they did that. And it's one of the best in situ measurements using the rain gauges. They produce the rain maps. This is the study people refer to monsoon rain in India, where southwest monsoon, how it is done in the year to year based on this climatological study. They did the study in 2006. They published a paper where they compared with the IMD data sets with the climatology data sets. Very good agreement, mean rainfall. They published paper, one of the best studies what they have done. But the thing is, it's all done using in situ gauge measurements. There is no radar in this one. 50 years of data, 2,000 rain gauges, all interpolated for about 100 kilometer or 50 kilometer grids. They did that. Now they compare with their data set with, again, climatology observations, the IMD data between 51 to 1995, the good correlation. These are fantastic studies. Followed with that is in Monsoon Online. This is I showed 2023 and 2024, two different monsoon, southwest monsoon period, where we got normal rain about 868 millimeter. 23, it's basically it's about slightly less, about less than 5%, compared to 24, about plus 7.62. And so this is all done using the 53 rain gauges placed in India, many places, area weighted. That's how they do that. This is a gold standard for IMD to show how the monsoon rain for every season. But all these things are mainly based on rain gauges. There's not much radar into this, what we show here. And so there is a lot of interest currently in India trying to do rainfall maps using the radar. Currently, what they do in India, NCM, RF, WF, they generate 3 different blended rainfall products. One of them based on satellite and a gauge. That's a 20 kilometer resolution, daily product, they do that. Then they have multi-satellite with connected with again a gauge. In that case, they have about 4 kilometer resolution, the second one. The third one is they have a radar blended product. Recently, they start doing this one, 4 kilometer. And if you look at all these things, there's a one common thing is satellite. Satellite is not a great instrument to look at the rainfall maps. If you don't have anything else like the ocean or the mountains, then satellite is quite useful, but not over the land. Land, current standard in most of the places are radar with the gauges. That's the standard. The satellite, in India, I used a lot of satellites, didn't have that many radars, say about 10, 15 years ago. Then the satellite was useful tool, but not anymore. And so IMD realized this, they're moving towards the radar blended product. So in this regard, what they produce is, this is blended with the satellite, the radar product, they show this one. And this is a very good technique or estimation what they produce it over the India using all the radars, about 37 radars with them, they do this one. But I'm not sure how much validation took place in this one. And so give a background, really what we can do, how we can improve the current product from IMD, what they produce it using a satellite and the radar. We have a lot of opportunities here. Rain gauges provide the direct, accurate rainfall, no doubt. And any radar, any rain map has include rain gauges, no doubt. Then the last 2 decades, radar has become highly desirable source of rainfall measurement worldwide. And so radar rainfall product is the best product to produce it. So in India, we have these are the products that do it almost every day. They have all the gauges. They code them with various color distributions here, with the red showing very heavy rainfall. Go back to green, the very light rainfall. Then the yellow is a moderate, heavy rainfall like that. Blue is a moderate rainfall. They have a fantastic gauge network. IMD Pune, the archive this, and they have a good in situ measurements. The key is how do you make use of this measurement to produce better rainfall product? Rainfall estimate using radar. There are many relations exist. However, it is not sometimes that easier to do with the radar also. Radar has other issues. First of all, what type of relations you use it? The Marshall-Palmer or convective rain, tropical rain? There are many different ZR relations exist. But for a daily rain, for a long-term average, it's not a big difference whether you use a Marshall-Palmer or a tropical rain. Both will give you similar relation for a long-term averages. And it's not that critical. But once we do that, still the radar measurements need to have many corrections. It has to be calibrated right. There'll be clutter effects, beam blockages, so many things. That's where the quality control of the radar product has to come play. This is not straightforward as a rain gauge measurement, but it requires good amount of work. Once we do that, we get rainfall product much more accurate, high temporal and spatial resolution. That's advantage. And more work has to be done to get a better product, because rain gauge alone won't give you that kind of spatial distribution. Once you can do with a good radar-based product, work with the rain gauges, then things will be much better. For example, in the National Center for Infrared Prediction, USA, they have a stage 4 product. This is a stage 4 evolved from stage 1. They use basically two things, gauge and the radar, nothing more than that. There's no satellite. I don't know why IMD uses satellite still now. I don't know why it is. Because the radars now, IMD has quite a bit of radars. They could use just using the radar and the gauges. That's what the product basically said, stage 4 in NOVA, what they produced it. The stage 4 data sets as a 24-hour hourly, daily, 6 hourly, they can do that. This one is a very good product. What they use it as they use this product to validate their satellite product. Goes the other way around, because this is the product from the radar and gauges. They validate a satellite, how good it is. But in IMD, I don't know why they use the satellite, use with that as a standard, mixing with that. Hence, this is time to work with improve the product using just radar and the gauges. Then there is another product, multi-radar, multi-sensor, MRMS, that uses various things, radar, gauges, satellite data, and numerical weather models. It's called reanalysis. It's a 1 kilometer product, high resolution. They can do that. But before we get there, it's important to do that ENSEP product, which is basically a radar gauge-based product. If you want to do that, you need to have very good quality control radar data. You need to have it. Then let me show an example of ENSEP, the NOAA product, what they produce. Here is about 500 kilometer by 500 kilometer. I show the ENSEP product from NOAA. This is a total rain for the year 2012, 13, 14, 15, and 16. You could see the variation in the rain, spatial variation in the rain product from 2012 to 2016. I mean, there are changes between, sometimes it's a maximum rains up to even 3,000 millimeter. This is the southeastern US, Alabama, Louisiana, southeastern USA, where I'm showing the product. There's year-to-year variation, shows very nicely captured by the radar and the gauges. Then the white dots, what you saw in the figures are various radars. Those radars are merged, composited, produce spatial rain. It's called basically stage 4 NOAA product. Here I saw basically the difference between two different rain products. One is from a stage 4, which is basically just using the radar and the gauges. On the right side, for the same year, this is basically from 2017, using high resolution 1 kilometer product. Look at, there are some differences, even though overall things look okay, but there are red areas. If you look at it, the large, heavier rain, which are much wider or more broader in the left picture compared to the right picture. And the resolution matters. What kind of data we use it matters. These are highly quality controlled, these products. And so there are a lot of opportunities improving the IMD rain product using the gauges and the radar. To do that, I mean, like I showed you earlier, we got the best gauges. We got a 37 radars. It has to be once we calibrate with a good data set, they can use just this radar measurements with the gauge measurements, can produce very good product. And if you want to do that product, the challenge is we got to do with the gauge and the radar comparisons. This is a table, I published this paper some time ago in JTech with Ed Brandes. We did 2 years of analysis using the gauge and radar. This table shows gauge and the radar. If you look at the S-pole is S-band radar, KFTG is a NOAA radar. Then if you look at the ratio, the gauge to radar, that is the middle column there, the ratio is sometimes greater than 1. That means radar is underestimating. That is well known in the radar estimate of rain. Sometimes underestimates, sometimes overestimates, but mostly is underestimates. And this is where the gauges will come in play to correct for the radar estimates of the rain. Once we do this right, it takes good amount of efforts, good quality control, then the products of rainfall maps will be much, much better than what we have it today. So it's my last slide here. There's a lot of work could be done for improving the daily rainfall map using the gauges and radar. Then that could be used to validate the satellite-based rain product. Then I'm in the process of working with RMC Chennai, see whether you can do the rain map for 100 kilometer radius from Chennai, just using a radar and the gauges, no satellite. And hopefully that could be validated using the valid satellite product. Then IMD, if they're working on the way in which working on the rain radar product, we could compare with them too at some point. Again, other place what we can do is in Bhopal, we have the ARTCI, where you have a lot of good measurements, could be done there also. So with that, I'd like to conclude here. I presented 3 different topics. The first one was on hardware, basically signal processing, radar signals. The second was how do you combine in situ to remote measurements? The application I showed was detecting rain formation from the cloud. The third one was basically on the rainfall map. So I'm happy to take any questions if anyone has any other comments. Thank you.
Thank you, sir. We offer our sincere thanks to Dr. Jyotiram Vivekanandan, sir, for his insightful and engaging.
Vivek,
Yes.
this is GV here.
Yeah, I can hear you.
Your last point about working at RMC Chennai for
Yeah.
100 kilometer radius.
Yeah.
I think there are some new radars which have been installed in that region. Okay, there is a C-band dual pole radar at IGCAR, and there is a X-band dual pole solid state transmitter radar. Both are solid state transmitter radar.
at NIOT, Chennai. And apart from the S-band radar, which is at Fortress building. So I think you should take this data, and most importantly, before you take the data, a good calibration needs to be done among these radars, and also the atmospheric correction for the X and C band radars.
Correct. Very good comment. Yeah, perfect. That is where real challenge is making use of these radars, what you mentioned. And thanks for pointing out additional radars in addition to IMD radar, the other, the new radars, the X-band and C-band radars. Then the calibration, the key, and the gauges, hopefully they are well maintained, well calibrated rain gauges. Then the Pune, I think they have the good database. That's what I was told. And thank you for that suggestion. And I'm hoping we could produce at least few days of rain maps, because to show how good the rainfall map could be at 4 kilometer just for daily rain maps. Thanks, GV. Thanks for the comments.
Yeah, another radar I forgot, that is a SHAR, S-band radar, which is now dual pole. Okay.
I see.
So, and also there is a fairly decent gauge network, which is a telemetry gauge network was established earlier. I don't know whether they're still there or not. Around
Yeah, you are right. They said about Dr. Amuda, she mentioned that the 45 AWS automatic weather stations, I guess, they have a good rain estimation, maybe a high resolution time, I guess they have it. That's what she mentioned that. Thank you. Yeah.
Thank you, sir. We now have the pleasure to hearing from our guest of honor, Dr. G.M. Srinivasa Viswanathan, former director of ISRO Telemetry Tracking and Command Network, who is commonly known as ISTRAC, ISRO. Dr. Viswanathan's stellar contribution to radar and space technology have set a benchmark for excellence. Now I would like to request Mr. Sharad from ACARR, CUSAT, to formally introduce Dr. G. Viswanathan, sir. Mr. Sharad.
Thank you, sir. Gauravaram Viswanathan, sir, started his career with Aeronautical Development Establishment, Bangalore, and worked on avionics systems for Indian Air Force. In 1970, he joined Tumba Equatorial Rocket Launching Station, Trivandrum, as radar engineer to develop tracking radar systems to support India's first satellite launch vehicle, SLV-3. He later on headed radar development project, which has successfully developed and commissioned 3 tracking radars in C-band and one tracking radar in S-band. G. Viswanathan sir, as project director, successfully commissioned the Indian MST radar system, a semi-active phased array, the second largest in the world, as a major national facility for atmospheric research in India, now at Gardanki, in collaboration with Samir. As Viswanathan sir, as project director, also successfully realized the first Indian Doppler weather radar in S-band to support Indian Meteorological Department. He has won several awards, including IETE IRSC Award, joined IMS IAF Award for Excellence in Air and Space Meteorology, and ISRO Award for Excellence in Weather and Atmospheric Radars, which was presented to him by then Prime Minister of India, Dr. Manmohan Singh. Over to you, sir.
Thank you, Sharad. Sir, could you please unmute? Yeah. Sir, welcome, please.
Thank you. I don't know whether my presentation is available with you, or I sent a mail to Abhilash. Can you just check that? Yeah.
Yeah, I will share it from here.
Yeah. Okay. So I'm very happy that meeting a lot of friends, including Vivek, and he has made an excellent presentation on how to make meaningful measurements of rainfall by merging the rain gauge data and the radar data. And a lot of what I'm going to mean, I'm not going to say much. Whatever little I'm going to say has already been said by Vivek, and let us see how it goes. Can you make it bigger? I mean, sort of project it. Can you go back? Okay. No. Next one. Yeah. Okay. I'm going to give a very brief introduction to the indigenous development of Doppler and polarimetric weather radar systems in India. And my colleague, erstwhile colleague rather, Srimati Anita will show all the radar systems which have been produced by technology transfer to industry and from ISRO, and that will be a bigger one. And I would, sorry. Okay, all this is already said by Vivek. So only thing is, important thing is the development of the radar for measurement of rainfall. Okay, using the polarimetric technology has become the hallmark of a standard kind of a thing. And IMD has been in the game from early 50s for using radars and for various applications. Okay. Including the cyclone detection and storm warning and things like that. Okay. The next one. Can you go to the next one, please? Yeah. So this is a view graph which shows a Doppler weather radar scanning a cloud system vertically. You can go either vertically or you can go around in scanning. And you can see the hydrometeors which are filling the radar beam and the resulting rainfall, which is below 1 kilometer, which reaches the surface. So this is just to show how it is in physically in the cloud. In fact, Vivek has told a lot more about it. Okay, next one. Yeah, this shows the spatiotemporal sampling of the cloud systems in a dynamic weather phenomena using the Doppler weather radar. It's a hemispherical volume coverage. I mean, ignore the bottom, whatever is not there. It's above the earth. Okay. So this is the radar beam, and this is the sort of a weighting of the radar beam, and the pulses, the radar pulses, which are transmitted by the radar and received. So this shows the, see, if you take the radar resolution elements, the beam width is one of the resolution elements, and the pulse width is the other resolution element. And of course, for Doppler, it is the integration time. So this shows the different pulses, interpulse period of t, number of pulses in a given second, given by the PRF, and this shows the cloud system which is sampled. So the infinitesimal volume, what we take for measurement, is given by θ3 into r, which is r is the radius, the distance from the radar to the volume, the resolution volume, and θ3 is the beam width, and delta r is the range resolution, which is proportional to the pulse width. Okay, so this delta V is what we sample, and as Vivek was telling, there is a lot of corrections have to be incorporated when you make rain measurement using radar. You can see this, one of the important factors is the beam broadening. As you go further away from the radar, the beam becomes larger. So there you have bigger dispersion of measurement, and that you have to reckon with. The next one shows the base products, which are actually the 3 moments of the time series we generate. The time series are generated using the radar pulse, PRF, and the precipitation intensity is what the first moment, 0th moment, which is the area under this power spectrum, total area under the power spectrum. The mean Doppler velocity of the hydrometeors, which are churning inside this volume, and that is given by this. And spectrum width is the dispersion of this velocity in that resolution element. So, so when we talk about as classical radar people, we talk about radar cross section. The radar cross section for a hard target is sort of the physical cross section, which is given by the optical region of the thing, whereas in the hydrometeors, which is in the Rayleigh region, and this is given by this. So the radar cross section of the weather targets is actually due to the it's a volume target, and we assume that the targets, that is the weather, fills the radar beam. That is why it's called a soft target completely. But this again has to be taken with a pinch of salt. As you go further away from the radar beam widens. So the radar beam may not be totally filled by the hydrometeors. So these are all some of the corrections we have to take when we make the estimations. So the cross section essentially is given by sigma, which is eta into V, and eta is the basic backscatter cross section per unit volume, and in the units is meter square to the meter cube. Okay, and eta is given by the summation of the sigma I, which sigma I is the backscatter cross section of any ith scatterer in that volume. Okay. Typically, you can take a raindrop kind of a thing. Next one. So you get eta as a summation of all the sigma i's over the number of drops which are in that resolution volume. So I'm telling all this to derive what are the parameters we measured, the moments. You can get the z here as the drop size diameter to the power 6 summed over n droplets which are in the volume. Okay, so next one please. So you end up with the range cell in which you are having the c tau by 2 is the delta R kind of a thing, and the phi and theta are the azimuth and elevation beam widths. Most of the radars, both phi and theta are the same, normally around 1 degree. Okay, so this leads to the power received from the radar PR. Next one, yeah. Next one, please. From the classical radar equation, where the different parameters are defined, like the power transmitted, the antenna gain, the wavelength, and things like that, the losses and stuff like that. So this PR ultimately gives the received power, which Vivek was telling in the range of about 10 to the power minus 13 watts kind of a thing. Okay, so we normally transmit like a megawatt of power in a vacuum electron device like the Klystron based transmitter, and in solid state transmitters we use lesser power but with a wider pulse width and use pulse compression techniques. So this is the famous Pubert-Jones equation for the weather radar, and this can be simplified like this, and these are all the various parameters which are taken into account. Okay. I think many of the textbooks give this, and already Pradhan and people like who my predecessors who have given lectures on the radar have covered this. Next one. So this is the typical signal to noise ratio performance we achieved for the indigenously developed radar system, first radar system. As per the IMD specifications, they wanted a sensitivity of 23 dBz of 500 kilometers. That's what we have got. And of course, as you go closer and closer, the signal to noise ratio improves. Next one, please. So this is a typical block diagram of the single pole radar, and it's again more elaborately described by Vivek earlier. And only thing is I want to highlight that the current trend is we don't derive the I and Q and then digitize them. We digitize right away the IF signals, okay, as the I and Q, and then we extract the various parameters from that. That is the modern signal processing. And we have a number of, sorry, next, previous one, please. Number of workstations where the different products are shown. So the attenuation due to rain is an important aspect. The top curve shows there is no attenuation. The next curve, the Mao region, is the S band, which suffers minimum attenuation. And the yellow, I think it is quite invisible, is the C band, this is the yellow curve. And X band is this curve, suffers quite a lot of attenuation due to rain. So that is why the X band radars don't normally operate beyond 100 kilometers. Typically, the data is collected over 50 to 80 kilometers. And the C-band radars cover up to something like 200 to 250 kilometers, and S-band radars are the longest. They go up to 500 kilometers, and they are typically used for cyclone detection and things like that. So we go to the basics of dual polarization in radar. Unlike transmitting one polarization, in fact, there's a lot of historical background on this. The WSR 88, which is the benchmark for the over 160 systems are produced in US. By mistake, they used vertical polarization to start with instead of the horizontal polarization. Because classically, people used to believe that the raindrop is like is of the shape of a teardrop. So the major axis will be vertical, but that is not so. Yes, you can see here, the raindrop is more like this. It's an oblate spheroid with the semi-major axis being horizontal. Okay, so that is why the horizontal polarization, all the single polarization radars use horizontal polarization to get a better cross section from the rain, and the dual polarization radars use both H and V polarizations. When you transmit H, get the both H and V, receive it, or you can alternate H and V and receive both H and V. Okay, these are the two modes of operating the polarimetric radar. The solid-state transmitter-based systems use the alternate thing, which gives a better estimation of LDR. And of course, these are the advantages of the radar polarimetry. Over the single pole radar, you can get, there are many scatterers in the atmosphere, not necessarily the raindrops or hydrometeors. Sometimes you get scattering from birds, insects, and we have seen at SHAR a number of occasions, birds giving, there's a bird sanctuary nearby. Birds give a beautiful cross section. We can see early morning the birds taking off from the lake, going and coming back in the evening and forming back to their nest. Okay, and insects also quite a bit of scatter comes. So it is not possible to distinguish this in a single pole radar, whereas in the dual pole radar, there are AI-based techniques to discriminate what is actually a non-meteorological scatterer. Okay, so the polarimetric radar also, please continue. I mean, the last one, yeah. So the polarimetric radar then reduces the impact of the DSD on variability and the quality of rainfall estimation. Okay, the shape and size and other information can be obtained from the dual pole information. This is true especially when you have snow, hail, and other hydrometeors other than raindrops. Okay. Well, with some caveats, polarimetric measurements are also immune to the radar attenuation, and it is the tornadoes are not very frequent in India, but in US there are terrible tornadoes occur, and the dual pole radars can detect the debris lifted by the tornadoes. Okay, next one, please. So as Vivek was mentioning, QPE, quantitative precipitation estimation, is a very important product, and the accumulation and hydrometeor classification are important applications of the polarimetric radar. And severe weather events like cyclones, thunderstorms, and tornadoes, of course, we can get an early warning. In fact, one of the driving forces for the establishment of the WSR 88 network and converting them to dual pole is the tornado warning. It gives a lead time which is sufficient for evacuation and giving the citizens a sufficient lead time to escape from the damage done by the tornadoes, especially loss of life. So other thing is sorry, please go back. The internal wind flow in the structure of cyclones to estimate the severity of the cyclone and assess the damages at landfall. Okay. Of course, the characterization of mesoscale weather systems and 3D visualization of cyclone structure are the other applications. Next one. Next one, please. Yeah. These are the base products of polarimetric Doppler weather radar. Single pole radars, like Vivek has shown the different ZR relationships for the stratiform rain, the convective rain, etc. So, in fact, there are lots of A's and B's, more than 1,000, depending upon the location where you are, the type of rainfall you encounter. So that is why it's not a very standardized thing. So, although Vivek has shown some 3-4 relationships, including the standard Marshall-Palmer. Okay, the dual pole radars estimate rainfall using KDP and ZDR essentially, plus ZDR and ZH. So these are the definitions I'm going to show. The first 3 are from the single pole radar. The next 5 or so are from the dual pole radar. ZDR is the differential reflectivity. 5dp, this should be up actually. This 5dp is here. That is the differential phase. And KDP is the specific differential phase, which is over the distance of measurement over which. The basic advantage of the polarimetric measurements is that they are actually, you measure the propagation phase corresponding to each polarization. So that is why it is slightly more accurate. And ZHV is the zero log cross correlation of the H and V. And LDR is the linear depolarization ratio. Next one, please. So these are the derived products from the radars, which are IMD is very fond of these products. Although these products help in situ, they are not really, when you have a network of radars, these derived products are not much helpful. It is the base products which are assimilated into the models and also creating the mosaics, national mosaic from one place, one end of the country to the other end. US makes it. Okay. Next one. Okay, this is the specifications of the S-band dual pole DWRs. Basically, for velocity measurements, it's about 250 kilometers, and for the Z measurements, it's about 500 kilometers. So the accuracy is conservatively given as 2 dB, and velocity is 1 meter per second. So the target will be to reduce this 2 dB to 1 dB by proper calibration. Okay, next one. Of course, the unambiguous velocities can be improved by pulse staggering and things like that. Okay, now I just want to give a story here. So the radar group in ISRO had finished. We had 2 groups actually. One was working on the tracking radars for PSLE, that is the PCMC radar, in collaboration with Bell. Another group was working on the MST radar to establish the radar as a national facility. So by 93, the MST radar was handed over to the users, and by that time the PCMC radar program was also over. So we were all relatively free. I took up some work for what is now known as JAXA. Earlier it was called NASDAQ, the Japanese space agency, for the TRMM. The TRMM is, as you know, a joint product of NASA and NASDAQ to develop a spacecraft to measure rainfall estimation. Okay, it's a very successful project, and which led to the now currently operating GPM. So at that time, I'm talking about 93, 94 time frame, when the internet was not very fast. Now we get fabulous speeds on the internet, and IISc had the best, fastest network, and you cannot go in daytime and get access to the IISc network because so many users will be there. So Professor Balki was in charge, Professor Balakrishnan was in charge of the Supercomputer Education and Research Center. Used to, a good friend of mine, used to call me at 9 o'clock in the night to use the internet. So I used to go there. I was doing some work on the ground validation of TRM. So I used to get some data and get some algorithms and things like that. So that time, one of the days, Balke said, hey, why don't you do a Doppler radar? IMD wants it. This is how the indigenous development started. That was the starting point. Then I made a proposal to Professor Rao, who was our chairman at that time, and he said, hey, why are you wasting your time? IMD will never buy an indigenous radar, they will only import. So, but I persisted. Then he asked me to go to IMD and make a presentation. I did that, and ultimately, due to the efforts of Dr. Kasturirangan, who succeeded Professor Rao, and then Dr. Ramurthy, who was the secretary of DSP at that time, and Professor Ramarao, who succeeded Ramurthy, they had a meeting and decided that ISRO will do the indigenous Doppler radar, and IMD will be allowed to import 2 radars. Okay, and this proposal was vetted by a committee headed by late Dr. Shranai, who was the director of LRD, which is the Defense Radar Center. So we had a PDR for the Doppler weather radar, which was again chaired by Dr. Shranai, and we had some eminent experts in the Doppler weather radar field, like late Digdoviak, Dusan Zinik, and Professor Chandra, whom all of you know. They participated, gave us a lot of inputs on how to do this. And ISRO realized this first single polarized Doppler weather radar, even though we made a feed which is dual polarized. IMD wanted single polarization, we did that. With the collaboration of national labs like NAL, for the radome, Samir for the 1 megawatt transmitter, and LRDE for the antenna feed. In fact, Anita, who is going to follow me in this lecture series, is the person who actually participated in the design and fabrication of the dual polarized feed at LRDE. She took it up as her ME project. Okay. And the first radar was integrated in Bangalore. It is like the camel at the tent. We took our antenna there to characterize it in the LRD test range. Then we asked the NAL to integrate the radome around the antenna, characterize the radome, and our own surprises. And then we brought the transmitter one by one, and the whole radar was integrated at Bangalore in 2000, and then shifted this radar to, after doing some trials, to SHAR, which IMD wanted this to be located in SHAR, and handed out to IMD after verification of the performance by a committee headed by Professor Mahapatra. Next one. So we had a lot of technical challenges. I want to highlight that because, you see, we get setbacks. We plan to do something, doesn't go according to that. Okay, so one problem what I encountered was the third side lobe of the antenna was higher than the second side lobe, defying general logic of how the antenna side lobe should fall. And then again, thanks to Balki, one of those days when I had a discussion with him, he said, hey, GV, you hide your antenna struts, which is supporting the feed. How do I hide the struts? So we went to a defense lab at Ambarnath near Bombay, who are capable of hiding a ship. This is the stealth technology they do. So we went to them, got the material which they coat on the ships, but that is tuned for X-band. We had to do it somewhat in a tricky way for the S-band because the material itself was becoming heavy. So we covered the inner surface of the strut and effectively hid it. So the third side lobe vanished. Okay, the radome Mark 1, when we characterized it at LRD test range, gave us enough headache. So this radome, we made it using pentagons and hexagons. And they made a systematic line source kind of a thing, which enhanced the side lobes, especially the elevation, which is not acceptable for us. The side lobe level we targeted was around 28 to kind of dB and minus 28 dB, and then this was increasing it. So then we used it for some time and solved the problem by going for a randomized larger panels in the Mark II. Anita will show those photographs. Okay. And this is how we solved the problem. It took a lot of time and we had a lot of fights with NAL. We are all friends and they stood by us. We fought how to improve it. They did a lot of work. They did tremendous amount of work in realizing this radome. First they said they will do a flat panel radome. Then we convinced them we can do curved panel radome. Then the second Mark II. It has been a tremendous experience. Then they gave the TU bell for making the radomes. The klystron-based transmitter with 70 kV, 8 kV was really a nightmarish thing. It will arc. So the cables were arcing, and we used to have a lot of ozone emission in the transmitter rack. And then we solved the problem by going to IISc electrical department, and they gave us they fabricated specially high voltage cables for us, which has solved the problem. And the med data products, IMD wanted so many data products based on the imported radar, and we had a handicap. We are not meteorologists, we are engineers. Okay, so first, our main problem was to understand the meteorology behind this data product to come to that. So that took some time, and also there were a lot of, even IMD didn't understand certain things. So late Sri Raghavan, the doyen of radar meteorology in this country, was the chairman of our committee. He has moderated it and seen that the data product had a rationale, and that's how we were able to generate all the data products which IMD wanted and give it to them. And then we did a first sphere calibration and comparison between the radar at Shar and the radar at Chennai. And we found that there is about the Professor Bhatt was the chairman of this committee, and there is a difference of about 8 dB we found. In fact, that is not surprising, because when I went to ROC, Radar Operations Center at Boulder, they told me, then when Dr. O'Brien was there, he spent 25 years only on characterization of precipitation. He said that two WSR 88 radars looking at the same cloud had shown 8 dB difference. then they had to work out what is the problem and systematically hit at it and calibrate. Next one, please. Okay, so then we went into the technology transfer to industries for joint development, and also the ISRO Bell joint MOU realized the S-band radar, and then they were also in dual pole. Even though it's first one was single pole, subsequent radars were dual pole, and also ISRO and Bell jointly developed a C-band dual pole radar with a klystron as a transmitter. And ISRO and Data Patterns jointly realized dual pole DWRs using solid state transmitters in C and X band. Anita will give more details on this. And based on this requirement for data products, Bell has given a contract to a company called Sankhya Systems in Bangalore. They have done a comprehensive software package for dual pole data products required by IMD, and that is now accepted as standard. More details will be given by Anita. Next one. Okay, the importance of calibration and validation mean that there is no amount of stress which you have to put. Every radar has to be calibrated. We have a heterogeneous mix of radars in the country. We have radars from Germany, radars from China, radars from India, radars from what is that place? Norway or so, and things like that. So each radar has its own estimation, and we'll have to calibrate the radar. Otherwise, we'll have a problem. So we did the exercise we did in between Shar and Chennai. We used signal simulation for Doppler and receiver parameters, sun calibration for the antenna again, and sphere calibration for the overall system. So data validation, like Vivek was mentioning, the rain gauge is the ultimate sort of source for rain measurement, because in actual what we measure in radar is the precipitation intensity. It's not the rainfall which is reaching the ground. So the rain gauge measures this. So there is a gauge factor which we have to always adjust. And this dropmeter gives the drop size distribution again on the ground, and this again gives a very good estimate of rainfall. Of course, satellite intercomparison with we did with TRMM, and we can do it with GPM and similar things. Next one, please. So this is the rain gauge network, and we can use the rain gauge network effectively for the calibration of the Doppler radars. Next one. This is the intercomparison with TRMO we did. Looks quite good, I mean the comparison, but the 8 dB is hidden in this. We could not do it very quantitatively. Next one. This is the vertical cross section of the DWR and the TRMM pass. It's a very dicey situation. We must have the radar operating, and there should be rain, and there should be a pass of the satellite over the rain region and covered by the radar. So we successfully did it once. Next one. So what needs to be done in India is my opinion. Okay. So we need to have the national network of not only indigenous, all the DWRs together, and periodic calibration has to be done. And we have to ground validation using GPM or similar spacecraft, and populate the airports in DWRs. We are trying to get a DWR to Bangalore for last more than 15 years. Not happening so far. And plan a comprehensive complementary spacecraft to GPM, which ISRO can launch with KU and the W-band radar. This is my dream. I don't know when it will happen. Next one. So thank you. Next one, please. Thank you so much.
Thank you, sir. Thank you, Dr. J.M. Srinivasa Viswanathan, sir, for your profound insight and inspiring us with your wealth of knowledge. At this moment, I invite all attendees to join us in capturing this memorable occasion with a virtual photo session. So we done it earlier. Maybe 2 or 3 persons already joined you, like Gajendra Kumar sir and other. I think that will be good. So I also request Raketji, please take a click.
Okay.
Asim Murati, Mr. Shalom, if possible, and Amit. Anita ma'am, please.
Hello. If there are any comments or questions, I would welcome.
Yeah, sir. There is a Q&A session. That time we will.
Okay.
And it is mainly about the merging of data.
Sorry?
Okay, we'll come to that question answer session.
Okay.
Anita ma'am, please. If possible, switch on your video. Amit, please. Nasim Muradi, please. And Mr. Shalom. Ready? 3, 2, 1, click.
I have done.
Thank you very much for your cooperation. After enlightening that first session, we move to our second esteemed speaker, Srimati Anita Daniel, the Deputy Director of ISTRAC, ISRO, which has expertise in indigenous radar development. Inside are sure to be invaluable. Now I invite Mr. Rajoy Revello from ACARR, CUSAT, to provide a formal introduction of Madam. Revello, please.
Okay, sir. Thank you. Good morning, all. It is our great privilege to introduce Srimati Anita Daniel Madam from ISTRAC ISRO, a prominent figure in the field of radar electronics, as the esteemed speaker for the valedictory function of the Radar Meteorology Lecture Series organized by SAMA and ACARR CUSAT. With a distinguished academic background, Srimati Anita Daniel holds a bachelor's degree in Electronics and Communication with honors from Government College of Engineering, Tirunelveli, and a master's degree in Electronics and Communication from the renowned Indian Institute of Space Science, Bangalore. Since joining the Indian Space Research Organization in 1988, she has made significant contributions to the design and development of advanced radar systems. Currently serving as the Deputy Director of the Radar Development Area at ISTRAC ISRO, Srimati Anita Daniel has been a core member of the team responsible for the commissioning of major radar systems, including the MST radar system and the polarimetric Doppler weather radar systems across the country. Her current projects, such as the development of Ka-band cloud radar and X-band phased array Doppler weather radar and the ISRO radar for orbital debris detection, reflect her commitment to the advancement of radar technology for the atmospheric research. Thank you, madam, for accepting our invitation, and we welcome you all to the talk on the topic indigenous development of radars.
Thank you, Dr. Now I'd like to
good morning. Yeah, good morning, all. Can you hear me?
Perfect.
Yes.
Yeah. I would like to thank, first of all, G. Viswanathan sir. GV sir, we used to call, for giving me an opportunity to be a part of this program. So let me start with my presentation. I think the GV sir has given a brief introduction how we have started the Doppler weather radar program in India. And I will just tell from what he has left. So I think this is the first S-band DWR SHAR radar which we have made indigenously. This figure I just want to show, which GB was mentioning. Our antenna was tested at the LRD test range with the radome installed. We were doing this test nearly for the nearly in the year of 1999-2000 range, and where we characterized the full radar system also. And these are all the radomes built. So you can see this is the Mark 1 radome, where we have more randomized, it is a very regular structure of radome panels. And subsequent to that, we made the Mark 2 radome, which is more randomized, and we could resolve whatever that side lobe problem which was manifested in the Mark 1 radome. And the next one is the X-band DWR radome. This is also a totally indigenous radome which we have done, and it is currently installed in NARL. So, so after this first radar, these are all the radars which ISRO has installed over different locations of India. So for this S-band DWR Chirapunji is the first Mark II radome, and this DWR Mark II radome was based on the technology transfer by ISRO. Bell has developed, and this radar, it is having a dual polarimetry capability, and the antenna diameter is around 9 meters. I'll go to that there. No. So this is the specifications of the Mark II radar. Mark II radar, which frequency is S-band, and the maximum range is 50 kilometers. It has an antenna diameter of 9 meters and a prime focus parabolic dish with a dual polarimetric feed. And radome is a foam sandwich spherical radome of 12.8 meter. And it has a solid state modulator based transmitter using high power klystron. And it has a low noise front end. And we have a comprehensive RF and IF simulation setup. And signal processing is using VMI based COTS DSP board. And our antenna servo can move from -2 to 90 degrees. And the radar operation is through a radar controller. And we have all the base products, ZV Sigma, and the polarimetric products. All the 6 products are also available. So this radar is it's operational from 2017 onwards. So this is the first radar, Mark II radar, which was installed in Cherrapunji. Currently, it is called as SORA. So this, you can, so some of the few images which was captured by these radars, just some animation I am just showing. Okay, these are all the Gopalpur also we have a radar installed, and this is the cyclone in 2019 which was captured. And this is one more cyclone. And this Cochin radar, which we have installed in sometime in 2017, we had a very good utilization of this radar during the Kerala floods, which has happened in 2018 time frame. So next radar which we have done from our division is the C-band Doppler weather radar. This is again a totally indigenous radar, and in collaboration with Bell. All the except transmitter, all the remaining subsystems were done by Bell. We have a klystron based transmitter which was totally done by our group. It is a 250 kilowatt transmitter, and remaining subsystems were done by Bell, and total integration, testing, and everything was taken by our team and Bell team together, and it is a joint development. And this radar is operational from 2016, and it is in the weather radar network of IMD, and it is providing a very good data also. So some of the products which I am just showing. This is a Oki cyclone which was observed by this radar, and it was data was used by IMD also. Yeah. So next one is the expand radar also we have done, and this we have done it for NARL. And first version is a magnetron based transmitter, 70 kilowatt, which was done by our transmitter group in radar development area. And subsequently, this was upgraded to a solid state transmitter, and now it is currently in use by NARL team. And this is the transmitter which you have done. So after having this one, we had an interaction with the data patterns, means industry collaboration with data patterns, where we have made this transmitter was replaced with the solid state transmitters. So 2 radars were made from during this period. So that is one at S-band and one at C-band, and another one as at X-band. This C-band radar is installed in Viravali, Mumbai. It is range is 250 kilometers, and the peak power transmitter is 4 kilowatt, and this was done by our team in collaboration with data patterns. And this is also part of this IMD network. So one more is the expand. This is installed in NIOT Chennai. This is also providing a range of data up to say 50 to 80 kilometers. I think I'm having some problem with that.
Picture will come maybe. You just keep it for a second over there. Maybe
Yeah,
it will
yeah.
come, because maybe due to huge size it is.
Yeah.
So it is 34 slide, no? Slide number
Yeah.
30. So keep for a few
Okay,
seconds.
let me come to the future perspective. So we are in the process of developing a phased array DWR also. So let me quickly show that few characters. So we are trying to do a X-band rotating phased array polarimetric Doppler weather radar at the X-band. So we are aiming say 100 kilometers only, and 150 maybe on the higher side. 100 and peak power of 4 kilowatt, and antenna design and all is in the PDR. We are in the PDR state. Maybe in another 1.5 years time, we'll be able to realize this phased array polarimetric radar. And our team is also working on some advanced signal processing algorithms to provide data quality and to reduce clutter and other related noise. And we are also working on some AI related and machine learning things to improve the data processing and analysis. And this calibration is one important thing for all these radars. Whatever we are doing, we are trying to establish an automatic calibration setup, at least for our radar parameters. First system radar calibration has to be done on a routine basis, at least twice in a year kind of thing. So we have established a setup which will be able to do a good radar calibration within a short duration. And we are also working on the validation of these products, whichever we are getting from these radars, using rain gauges and LPMs. That is also we are just working on that, working towards that one. So with all these radars and things, this whatever mentioned by Professor Vivekananda and GV sir, this calibration and validation is one important activity which requires a joint effort from both IMD and our team also, with which we will be able to deliver a good output. I think I thank everyone for providing me this opportunity.
Thank you so much. We extend our heartfelt thanks to Srimati Anita Daniel Madam for her enlightening presentation and for sharing her valuable expertise with us today. With the completion of today's insightful lectures, now it is time to engage in interactive question answer sessions. Kindly, all of you, feel free to submit your query in the Q&A box. The session will be moderated by Dr. Swagata Paira from BIT Mesra and Dr. Dibya Prakash from Purnima University, Jaipur. We would look forward to your valuable queries and discussions. Q&A session moderators, please take part.
Yeah, thanks a lot, Dr. Mohan. So Dibya, you can start from the.
Yeah, thank you, sir. So there is one question. New dual pole H-band radar, will it give improved rainfall estimation compared to S-band?
Can you repeat the question?
Dual pole X-band radars, will it give improved rainfall estimation compared to S-band?
I think it is to TV regulations. It is to Vivekanandan, sir, I think. It is.
Oh, okay.
It's
Yeah.
11.
Okay, I'm happy to answer that. Dual pole technology gives one of the biggest advantage of dual pole is data quality. It's compared to just a Doppler weather radar, dual pole, since we have a polarimetric measurements, whatever the frequency is, the X band or S band, because of the dual pole, the calibration, like what GV mentioned, Anita Daniel mentioned about the calibration. That is a very key component. Without the calibration, radar measurements are not that much useful. Hence, calibration is little better using a dual pole measurement because the clutter detection could be done much easier. Dual pole because of additional variables using a FDP or the phase measurement, the ZDR. We can do two types of calibration radar needs. The first is a electronic calibration, which is done engineering within the lab, whoever does the manufacturing. That is a thing done all these amplifiers, talking about all the subsystems. Then comes the end-to-end system, the radar, when it does measurements in the rain, there itself you got the calibration has to be done. And very standard technique exists nowadays using a rain as a calibration medium, the dual pole technique that could be done. Then electric calibration within the engineers, what they can do. And without those two calibrations, the radar measurements is not that useful. It's a quantitatively, if you want to use it, radar has to be calibrated within the plus minus 1 dB performance. Without that, because if a 1 dB error gives about 18 or 20% error in rain estimation, the bias. And so that is well known, all these things. And calibration, what GV mentioned, it's a very key component to do that with the radar observations in the clouds and precipitation.
The second question by both Shuel Khan, second and third. The main question is that, sir, this process of data merging of radars can be automated?
To whom is the question?
I think it is again to Vivekananda sir, the same time,
Okay.
11:21.
Okay. If I understand data automation, we're talking about the baseband measurement, I and Q data, which is the basic of any data set from the radar. From there, if you want to automate any of the processing, computing, either your spectrum technique or pulse pair technique, there are well-known technique. All the things nowadays could be done electronically. It's not a problem. But there is one issue. There are issues with respect to anything, the bias, phase errors. These are things we have to understand. Hence, the automation comes once we understand every subsystem to the nth degree. We have to understand that part. Then data automation could be done. Then data quality is a totally different thing. Data quality is a total different topic than data automation. Data automation is talking about producing the products, mainly in the radar products, and storing them, displaying them. And that could be done with a good software and engineers and the Sankhya and others people mentioned about. They have done, I think, a good job in India to do some of those data processing and data movement computations for the radar systems.
The same question even asked by the host, also Rijoy Rivelo and Shuel Khan, that about the calibration, how the calibration is done by analyst. All that calibration is done how by analyst. Or the other way, the question is, please elaborate on automatic calibration of DWR.
Who is supposed to answer?
That's it. Let's ask Vivekanandan sir. When Vivekanandan sir will give the pass, I'll come to you, sir. Yeah.
Okay. I'm sure GV can elaborate on this one. There are number of calibrations, like I mentioned before, the transmitter, the receiver. Receiver alone, if you want to calibrate, you can look at the sun, solar calibration, they call it. Sun, we know exactly how much power we get, a flux measurement, very well known. In the solar calibration, just in the receive mode, radar receiver could be calibrated with very precisely with using a sun as a source, the blue sky when there is no rain. That's the one part. Then next part is now you can have hot targets like balloons or known spheres, calibration could be done. The third part is having the measurement in the rain itself with the gauge. We can calibrate the radar because once we know the gauge measurements, how accurate we can do it, the polarimetric measurement, we can retrieve or estimate phase measurement from the power measurement. It's possible. Number of papers exist there. Rain itself as a medium, we can do that. And the three different calibrations are very standard. One of them using a solar calibration for the receiver. Then using sphere calibration that transmit receive, just single point. The third one is rain itself as a calibration target, where we can derive the phase measurement from power measurement. Because phase measurement is independent of any calibration because phase is a ratio between two signals. It's independent of any bias. And so we can do the calibration. And so this is a very standard way how we can do it within plus minus 1 dB for reflectivity. For a polarimetric measurement, for a ZDR, we got to do less than 1/10 of a dB or 2/10 of a dB has to be done. Then if you do the phase measurement, it should be done within a plus minus 3 degrees. And these are the very standard in radar, weather radar measurements.
Thank you, sir. The next question by S.V. J. Kumar. I'm just changing the question.
I'm saying if GV wants to add something, the calibration, Anita could add to this. GV, go ahead.
No.
Okay.
So, shall I proceed or Viswanathan sir, are you going to give some inner part of the calibration?
No, okay. But what Vivek told is fine. Only thing is the sun calibration takes into account both the antenna and the receiver. Okay, the antenna again also comes into the picture. And sun's emission is very well known. The data flux measurements are available for a given day, for a given location. Okay. The other uncertainties are about the transmitter power, which can be measured actually. Especially with the solid state transmitters, it is very easy. And even the high power transmitters, we can measure it to about dB kind of a thing we can measure. Okay, even better we can measure. Okay, and the raindrop calibration, what Vivek was mentioning, you have to take light rain where these drops are spherical. Okay, then that's a very good source for radar calibration. And the rain gauges do measure the rainfall, and that gives the system level calibration. Anita, anything you want to add?
We are having a bore site antenna also, which we will receive both V and H power, and we'll try to do the other calibration things also to add it to. Bore site calibration also, we have a transmit and receive in both vertical and horizontal, and we are doing a calibration at the radar end also.
Yeah, that is a luxury which IMD, I don't think they have it.
Yeah,
it's good to have that anyway.
So, what Anita mentioned, like basically you have a horn antenna some distance. From there you can receive mode, you can do it also. Patterns could be done. Now, given this much of discussion in the calibration between Anita and GV, I thought it's important IMD or whoever wants to do this, form a team. The calibration is a key for any radar, so that could be well established within IMD itself. That is quite useful. Without the calibration, the data is not that useful. That's a problem.
So we will ask that question little later. Maybe we can ask that time Gajendra Kumar sir or Devendra Pradhan. But now let's complete the question answer with you three. The next question is, what are the limitations of dual pole? Do the dual pole radars one-stop solution for our mesoscale studies?
Okay. Dual pole radar, it's better than single pole radar. There's no doubt, because matching two channels where you got a microphysics between ice and liquid, you want to estimate, that's the only way we can do it. And lot of advantages. And so dual pole, as at least it's good or better than a just single pole radar. And now comes S-band versus X-band radars, which is like a C-band. I mean, Anita mentioned X-band and C-band radars. There comes a bit of a issue with all the attenuation, differential attenuation. How do you compensate all the things in the X-band and C-band? That has to be addressed properly. Otherwise, for any given frequency, whether it's a K-band or S-band or a C-band, dual pole data is better than single pole data. Of course, the dual pole costs a little bit more because the two receiver system and all the maintenance and calibration, that's all added, work. But it's a much better system. And so no doubt, all the radars, I'm hoping, in India will be converted soon with the dual pole, I guess, as per the plan.
So by one line sentence also, that is it a one-stop solution for our mesoscale studies?
Oh, the mesoscale studies. Okay, I'm sorry. Mesoscale studies are, if you're thinking about heavy-duty thunderstorms, like you're talking about huge hail or lightning or tornadoes, strong winds like that. Then also talking about cyclones, severe cyclones, heavy rain. Then they are talking about sudden downburst. Like you got a hit, like all the rain which happens in, say, 1 month, it falls in 1 day. These kind of events, dual pole is must, because dual pole data gives a much better accurate estimation of rain, flooding forecast, lot of things. It's a mesoscale studies which involves very transient, where things are very severe, time limited, 5-10 minutes, you got a heavy rain and the thunderstorms, hail detection, all those things. Dual pole data mesoscale studies are much more valuable than a single pole radar. And so in US, in 95 onwards, they converted most of the radars to dual pole radars. That data quality is good. Then mesoscale studies are much better using dual poles measurements.
Okay, the next question, I think it is already, we have answered that. Please elaborate an automatic calibration of DWR. So, if
that
any of,
already discussed, I think.
yeah, it's already discussed. So now it's another question, but it is in a sentence form. Phase shifter degree resolution being used in phased array DWR. I think it is a question, but so the question is that phased array DWR reduced phase shifter degree resolution. I mean, I'm not clear about the question actually.
Yeah,
Okay, maybe
question is,
I could interpret the question. Maybe the person asking about phase array radar, the phase shifter. Because phase array radar uses the phase shift to steer the beam.
Yeah.
And what is the quantization? Typically, the phase shifter, Anita could comment on this, the phase shifters usually quantize to certain degree. It's a 5-bit phase shifter, very common. Anita could add to that.
Yes, sir. We are planning to use a 5-bit phase shifter.
Yeah, yeah.
So,
It's,
ma'am,
yeah.
So, ma'am, you have a direct question also. Cannot we use electronic beam steering for phased array, or do we need rotating phased arrays?
Let Anita answer that. I could follow up with that.
I think it is, see, whatever X-band phased array which we are planning, it is having both electronic and mechanical also. See, what we require in our DWRs is, say, 20-degree volume scan coverage is required. So what we are planning is that elevation step, we are having two steps from 0 to 10 degree. We are having one step using a mechanical rotation. And again, the remaining things will be phased array scanning. Means we are having two azimuth elevation steps, 0 to 10 degrees. We'll have one coverage, and then again one more step, volume full coverage of 20 degrees using phased array scanning. Means we are having both mechanical and electronic steering also.
Thank you, ma'am.
So,
Yeah, well, let me add to that. I think now let me add to that. In a phased radar system, doing both, there are two angles. One is elevation, or is a PPI, azimuth. That's all. Two types of scanning has to be done. Phased radar system, there is one issue. If the beam goes away from the bore side quite a bit, the gain is reduced, beam is become bigger. To avoid that, what they do is, they do electronic scanning in the elevation plan, or elevation plane, I'm sorry, elevation. Then in the azimuthal plan, they do mechanical scanning. And that's very standard technique. And so you do 1D phase scanning, not 2D phase scanning. 2D phase scanning could be done, but it's a lot more complicated at this point. Is that, Anita, is that okay, what I added to that?
yeah, yes, sir. We are having a combination of both to see
Correct.
that we are meeting the volume coverage requirement of the DWRs.
Correct.
Okay, can I add something? So even in the azimuth, a limited phase scanning can be done with the mechanical scanning as well. Like
Correct.
the, yeah.
Thank you. I think the next question is also type of calibration related. How do they overcome blending of data from a suite of various types of radar in order to integrate them for a holistic picture over the country?
Okay. See, we have to consider two things. First of all, let's say same type of radar. We got all S-band radars, 3 gigahertz radar. Okay. Even merging those radars, creating a composite, is a lot of work, because each radar calibrations are different slightly. Got to merge it. Then comes the next point. You got the X-band radar and S-band radar. Then what happens? That's the next step. And so this is a challenge where engineers could solve the problem. It is not that complicated, but it requires a lot of patience and work to do that. It's possible, but it's an engineering problem. It's not a scientific problem. Could be done. I think Devendra Pradhan had a answer, I guess.
Yeah, and also he raised the hand, so I was just thinking to ask him later. Yeah, so yeah, sir, please the question.
Actually, I was very curious to know something from Professor Vivekanandan, sir. Sir, this is my experience that when we are using the single polarization in S-band, C-band as compared to X-band, there is an overestimation of the dBz values whenever we are going from the thunderstorms here. So single polarization, when we are having S-band, it's my observation that it has got a lot of overestimation of the clouds and the rains and others as compared to C-band and X-band. Probably you agree, sir, here, I think.
Let's say you are saying that S band is higher than a C and other wavelengths. Okay.
Yes, sir. I found that whenever the radar is having the estimation of the rain and the cloud dBz values, the observation from the S band are slightly overestimated as compared to X band. Because, sir, in New Delhi, we have got all the three types of the bands: X band, C band, and S band. So when I compared the reflectivities of the same cloud in X band and C band, so I found that X band is reasonably good. C band is also equally good, but S band is having the overestimation. So, sir, my basic question starts from here.
Are you compensating for the attenuation in the X and C?
Yes, sir. Sir, everywhere it has been done. But again, the observations showed that there is an overestimate of dBz values corresponding to the rainfall and others here. But sir, if you are just converting them to the dual pole system, X band, dual pole, C band, and S band, so will there be that will be the solution of having the almost the same kind of the estimation, or it will be having the overestimate again in S bands?
Pradhan
Okay.
Sahab, Vivek, 1 minute.
Yes, go ahead,
Pradhan,
GV.
Pradhan Sahab, your C
Sir.
band is a dual pole, Delhi.
Sir.
Are you utilizing the C band dual pole data or single pole data?
Dual pole data, sir.
Then that should be accurate. How does it compare with the X and S single pole?
Because in the New Delhi, sir, X band dual pole is also there and C band dual pole. Both the dual pole systems are there. X band has been installed by the Astra Microwave, and C band by the Vaisala, Finland, sir.
Okay, I know X band Astra. Okay. Now, when all the estimates are properly done, is the question, including calibration.
So calibration has been done nicely, systematically, and it is being done again and again. But my observation was that C band and S band S band is having much more overestimation over the X band, sir. So if you are using this S band dual pole and C band, and so will this be the solution of having almost a similar estimation in all bands, sir?
Yeah. Let me step back a little bit. Do these radars have a radome?
Yes, sir. All these three are having the radomes.
Okay. If there are, okay, the radomes are there, there could be issues with the radome attenuation sometimes. If it's raining on the radome, wet radome, we got to be careful with that. And so that could cause some additional attenuation, and that has to be compensated properly. Maybe you did that. Okay, that is a one part. The second part is at higher frequency, the scattering is basically it's basically going to be more like a me scattering if it does really big particles. But in India, the raindrops are not that big because most raindrops are in tropical countries smaller than what we get in mid latitudes in general. And getting that me scattering, it's not causing any over measuring the dBz values. And I would say if you have all three polarimetric data sets, commonly if you look at the same volume, what you did, compensating for attenuation using the ZDR and the FDP, if you did that right, then it's a good way what you try to do it. But if it doesn't match, then there is some issues with the other wavelength. Because S-band is very good. S-band is we got to rely on S-band. It's less attenuation. It's a Rayleigh scattering, all the things. And we got to use S as if S-band is well calibrated, then use that as a benchmark. See some issues with the other wavelength radars. It could be done. And if you have some analysis done, show me some figures. I could comment on that. We have done some studies like that. Yeah.
Right, sir.
Yeah, it's a nice discussion. So
Thank
we
you,
have
sir.
one more questions, and it is related to artificial intelligence.
Swagata, actually, T.N. Rao sir raised his hand earlier.
Okay, I missed it. Yeah, T.N. Rao sir, yeah. Sir, please proceed. You are mute now.
No, I have not raised in my hand. I just
Okay.
I logged in again. That's it. I was
Okay.
watching from the beginning, but then in between some power off. Then again I logged in. So I think I don't know how it came.
That time you raised your hand. That's why.
No. Sorry.
Okay.
Okay, so this question to Vivekanandan about artificial intelligence. Please elaborate on influence of artificial intelligence in dual polarized DWR data interpretation.
Okay. The AI ML, currently artificial machine learning, become a very common thing most of the places. We use AI ML almost all the places, biotechnology, electronics, manufacturing, stock market, everywhere AI ML is used. But we have to be very careful. AI ML uses neural networking. Neural networking, so many neural networks exist there. neural networking is more like a black box. You got the neurons, you got the hidden layers, then you got basically how it's calibrated. Each neuron, there is some gates they used also. If you look at RNN, CNN, then so many neural networks are there. And it is not that AI/ML won't do the work. The real question is why it does work. That is where the real problem is. There are three things in the science: the why, what, and how. Neural network or AI can do something much more better because a nonlinear process estimation could be done. But we got to explain it, why it does it. If you understand the why part, then it becomes a very powerful tool. If it doesn't work, then we keep moving more neurons, more layers. It is not going to help because it's a black box. And so given that AI/ML is very prevalent, and so many things could be done if you do it right, provided we understand why it does work. And that's the real challenges. But to summarize, sorry, I went to a long answer here.
No, it's okay.
If you are using AI/ML, then we got to select the right network. For example, image processing, a type of network does image processing. A time series or like a missing data sets. That's for a time series like a LSTM, long and short-term memory network. And this thing has to be done. If you have some courses in data science, I'm sure they teach these things nowadays routinely. And so you can learn quite a bit using AI/ML, provided you know how to understand the data itself. Then also you could answer why it does work. If it doesn't work, you should understand why it doesn't work. That's a challenging problem. Everyone faces the same problem like that. It is not, that uncommon.
So now there are no more questions, only one request, who has already asked 2 questions. So I could say that enthusiastic Suel can ask that, sir, if you have any paper on the radar data merging and its calibration, please share that with us. So I think it can be done later if it is there. That much I can say. Or if you can give some ready-made ER or the title of the paper, you can listen from here itself.
I have a comment. In Anita's presentation, I noticed that the minimum detectable signal or noise floor, I guess, minus 140 dBm, 140 dBm. That seems to be quite low. Usually the range is around minus 110 or 115 dBm.
I think it should be 140 dBW.
Okay, dBW. Okay, that makes sense. Okay, got it. Okay, thanks, JV, catching that. Yeah, I was surprised
Question
about it.
and answer is over from my and Dr. Dibbapurga's side. So now it's over to Dr. Mohan.
Amazing. It is really amazing and very engaging session. We would like to extend our sincere thanks to the question answer, both moderators, experts, and participants for their active engagement and contribution to these interactive sessions. Your valuable input has made this a truly enriching and experience for all. Now, time for listening from the toppers. Maybe by this time you know that the result already been published. So there is a very good score. It means a participant engaged with all the lectures very much. Obilaji, you already published or you plan to publish? You will share the results now?
Marks is already shared. We
Okay.
will share by email the
Okay,
certificate along with the results.
Okay.
Yeah.
Dr. Abhilash and Dr. Tyagiji and Vivek, I must leave now. Thank you very much. And nice that I could meet all of you virtually. And
Thank you, sir.
Have a nice session. Thank you.
Sir.
Namaste, sir. We are almost end of the portion. I think couple of
Thank you very much.
Now we would like to hear the thoughts and insights of our top 3 performers. We kindly request each of you to share your opinion on the key takeaways from all the sessions, including today's as well. How this experience has contributed to your academic and professional journey. Your perspective will undoubtedly inspire and benefit all the participants' audience. So first is the MD Amit Hassan from Bangladesh. Amit, please.
Thank you, sir, for giving me the floor.
Can you switch on your video, please?
Good noon, everyone, the respected organizers,
Can you switch on the video?
speakers,
Can you switch on the video, please?
Participants.
Amit, can you switch on your video and
Okay,
stop your YouTube channel if it is running?
Thank you, sir. Good noon to everyone, the respected organizers, the distinguished speakers and esteemed participants. I am Mohammad Amit Hassan from Bangabandhu Sheikh Mujibur Rahman Meteorology University, and I'm a student of BSc in Oceanography. And it is a profound privilege to address you that we celebrate the culmination of the radar meteorology lecture series. I extend my heartfelt gratitude to SAMA, ACARR, and the visionary speakers who made this program a transformative learning experience. The insights shared have been truly inspiring, broadening our understanding of radar meteorology and its diverse applications. This series has not only deepened my academic foundation, but also enriched my practical perspective, preparing me for meaningful contributions to oceanography research, and besides, earning a commendable grade stands as a testament to the program's exceptional quality and the dedicated support of its organizers. I am especially grateful to Dr. Mohan Kumar Das, Joint Secretary 1 of SAMA, for recommending this opportunity. And also, I am grateful to NOAMI Bangladesh for fostering a spirit of interdisciplinary exploration among emerging researchers. As a student of oceanography, I humbly suggest to SAMA to consider organizing a future lecture series on marine meteorology or ocean atmosphere dynamics, incorporating practical elements to further elevate the learning experience. Finally, I convey my sincerest appreciation to SAMA, ACARR, and all the contributors for the unparalleled opportunity. Wishing everyone continued success in these endeavors. Thank you, everyone. Thank you all.
Thank you, Amit, and congratulations to you for your the best position. We can applaud Amit for his excellent achievement. Next is Mr. M.A. Dinu Milusha from Sri Lanka.
Dr. Mohan, he disappeared. He was there, but now he is not.
Okay. And next. Okay. I think Ovilaj, you need to mute the microphone. My echo is there. Okay. Next is Wendan Arsin Flavian Dambia from Burkina. We have seen initially, maybe not available now, right? Flavian Damiba. Maybe not. So I think we can go for vote of thanks, right? Okay. As we draw to a close, I invite Dr. Srikala PP from ACARR CUSAT to deliver the vote of thanks. Dr. Srikala has been a vital pillar of support throughout this program. Please proceed.
Thank you, sir. Good afternoon, everyone. I feel honored and privileged to have
I think
The
there is a
opportunity to
you.
propose the vote of thanks for the valedictory function of the 21 weeks online lecture series on radar meteorology organized by South Asian Meteorological Association and Advanced Center for Atmospheric Radar Research, CUSAT, on behalf of everyone present today. First and foremost, I would like to express my deepest gratitude to Professor Someshwar Das, Secretary, for delivering the warm welcome address and setting the perfect tone for this event. The successful and smooth conduct of this online lecture series would not have been possible without your constant encouragement and guidance. Thank you, sir. I would like to express our deepest gratitude to AVM retired Professor Ajit Tyagi, President of SAMA, for his thoughtful address and highlighting the significance of our gathering. Your continuous guidance made this event a successful one. A sincere thank you to Dr. S. Ablash, Program Coordinator, for providing a brief overview of the entire program and presenting it in a comprehensive manner. I take this opportunity to thank Dr. Devendra Pradhan, Chairman, Advisory Panel, for the thoughtful address and your invaluable guidance for the successful conductance of this lecture series. I would like to extend my heartfelt gratitude to Dr. J. Vivekanandan, NSF NCAR UCAR, for sharing his valuable insights on the advancements in radar meteorology. I'm sure that your deep knowledge in this field broadened the participants' understanding of how radar are used to study the cloud microphysics. I would like to extend my sincere thanks to today's guest of honor, Dr. G. Viswanathan, former Director, ISTRAC, ISRO, for his enlightening talk on indigenous development of radars. Your profound expertise in this field has significantly deepened our understanding. Thank you, sir. I also extend my heartfelt thanks to Srimati Anita Daniel, Deputy Director, ISTRAC, ISRO, for your thought-provoking talk on indigenous development of radars. I would like to express my gratitude to Dr. Rohini L. Bavar and Mr. Sharath Krishnan S. and Mr. Rijay Rebello for providing such a nice introduction about the today's speakers. Sincere thanks to Dr. Swagata Paira and Dr. Divya Prakash for moderating the question and sessions and for ensuring that the interactions were meaningful and engaging. My heartfelt gratitude goes to Dr. Mohankumar Das for expertly moderating the session and ensuring the proceedings remained organized and on track. Finally, I would like to thank organizers of the program, our distinguished speakers, esteemed audience, experts, for your invaluable involvement for the successful conduct of this program. I also want to extend a special thank you to all participants who joined us throughout the series. Your engagement, thoughtful questions, and enthusiasm have played a key role in making this event a success. Finally, as we conclude, let us take the lessons and insights we have gained throughout this series and continue to apply them in our professional journey. Once again, thank you to everyone who made this event a success. Wishing you all the best in your future endeavors. Thank you.
Thank you so much, Dr. Sikala PP. I think you delivering the vote of thanks with such grace and eloquence. Your words perfectly captured the essence of today's event and beautifully acknowledge everyone's contribution. With this, we conclude the valedictory function. I extend my deepest gratitude to our speakers, participants, and organizers for making this event a resounding success. Let us continue to collaborate and innovate for a brighter future in atmospheric sciences. Thank you all and have a wonderful day ahead. Thank you, sir.
Thank you very much. Thanks. Thanks to all.
Thank you.
Yeah, it's a nice journey. Thanks to all the organizers.
Thank you.
Thanks to Dr. Vivekanandan. He is still awake. He's past midnight in America, I know. But see the spirit, see the spirit that he would like to help us in this field. Thank you so much for being presented.
Okay, it's past midnight. The past midnight, but thanks for the opportunity. I mean, I enjoyed really, having discussion, presenting it. I learned a lot preparing for this talk. And so thank you for the opportunity to participate in this wonderful SAMA radar meteorology series. Thank you very much.
Thank you.
Thank you, sir.
Just one. Sir, please.
Thank you so much, and we continue to look forward of your support to SAMA because we may have refreshers programs on radar meteorology in a time to come, and we'll request you to guide us how to go about it to plan something which is happening new in the radar meteorology. Thank you so much.
Thank you. Appreciate that.
Lastly, sir, in continuation with Professor Tyagi, sir, I also request the President, Sama and the Someshwar Dazi, that we should have a refresher course with some typical case studies related with the dual pole radars. So in due course of the time, we can have some case studies and more understanding in-depth studies of the Doppler radar interpretation, of echoes interpretation and others. This is my suggestions. Thank you very much, sir. Thank you, Anita.
Yeah, one point to add, because most of the participants were suggesting physical presence and the physical interaction with the audience. Maybe Sama can look forward to having a physical meeting, clubbing all domains somewhere. We can host a physical meeting for 1 week or 2 weeks to have all domains to interact physically. We are happy to host that also. Thank you.
Yeah.
Professor sir will now communicate, sir. There is a physical.
I was just thinking that, let's hear from one of the EC members, Mr. Nasim Muradi from Afghanistan. He has been present throughout, though I know that still Afghanistan probably doesn't have radar, Doppler radar for their weather forecasting. So, Nasim Muradi, please, yeah.
Thank you so much. Good afternoon, my colleagues. First, I would like to thanks from the SAMA conduct radar meteorology lectures. It is more important for all members country. And I suggest that further capacity building from different field of meteorology from SAMA. Thanks again from all SAMA and SAMA members and for all presenters and participants. Thank you so much.
Hello, Nasi.
Yes, sir.
Yeah, we would request you to send us an email, something, you see, commenting upon our training program and anything which you would like us to take up. So
thank you so much.
Yeah, so if you write to us, we can put up this to our various funding agencies, that there is a demand to have a physical workshop from the member countries, and hopefully it will help us.
Thank you so much for kind support. AMD support always. IMD support always. AMD department. Thank you so much, sir.
Welcome, sir.
See, Tyagi Sahib is already driving. We have probably
prolonged it
so much that he is driving on the road, and GB has already left. But it has been a great session.
So, but we have to now, good suggestion has come, Somesh, to have a physical part. And let's the Vilash and Pradhan Sahab take a lead to develop a project proposal to the MOES or somebody to support this activity. So this will be a very good take away from this validatory function, and also for our future plan for the radar. So this is very important and a very good suggestion. So we should work on it. Thank you.
Thank you. Yeah. By the way, I think next lecture series is likely on the atmospheric dynamics and its application towards the weather and climate modeling, likely to start from middle or third week of January. So that is in the pipeline. And that will be the 5th lecture series by SAMA. Pune University has kindly agreed to be the host partner for the next lecture series on atmospheric dynamics. So this is just a pre-announcement, I should say, of the lecture series. Thank you so much. Dr. Vivekanandan, I think we have not met, but I know that we have been working at ACARR, where I visited in 2003 and 2004. Probably, I heard that you were there in the radar division, but I never had opportunity to meet you personally. So it's so nice. I'm glad to see you here. Thank you so much.
Thank you. Next time, please let me know so that we could meet whenever the opportunity is, either in US or in India or wherever we could meet. It's not a problem at all. Thank you.
Yeah, we used to interact a lot with GV and Professor Chandrasekhar when they were designing the first radar of the ISRO or indigenous radar in India. And my interest was particularly on the application of Doppler weather radar data in the assimilation of the NWP model. Dr. Pradhan Sahab was at Kolkata and he provided us sample data. Also, we got data from Chennai and also GV. I mean, he was still designing the radar at ISRO, but he provided us the data of the reflectivity and the radial velocity for us to test how to assimilate that in the NWP model. So they were all now history. They are all now history, but it was really very, very good to interact with them in the initial stage of the application of Doppler radar data in the NWP model in India. So it was a great experience.
Correct. Like a follow-up with your comment, actually, for weather radar, I mean, lot of people from India contributed for US, in US, I'm saying that. They did a fantastic work. Many people like that. And so we have a long tradition who contributed so much into radar meteorology and radar development. And so we have a rich heritage in US and Europe, and people from India. They did quite a bit of work. And so we could be very proud about what we did, and we could make it even better in India.
Sure, yeah.
Yeah.
Thank you so much.
Thank you very much. Thanks for your comment, and thanks for organizing it. We really enjoyed that one.
Thank you.
Thank you, sir. Thank you very much, sir.
Thank you very much.
Okay.
Bye.
Thank you.
Bye.
Thank you all. Okay.
Thank you so much.
Okay. I know. Thank you.
Mohan, can you stop the streaming again? Mohan already left.
Yeah, Abhilash.
Sir.
Thank you so much to and your team, and would like again, I had requested you earlier that entire team should become member of SAMA. We don't want to lose such good, and I'm sure they will find a lot of opportunity to interact and benefit from their association with SAMA. Okay.
Okay.
Thanks to Sri Kala, Rakesh, and all entire team also. Thank you so much.
Thank you.
Thank you, Dr. Abhilash, sir. Your team has done the, what should I say? I cannot express in the words, beyond the words, the work has been done by you, yourself, and your team.
Yes,
Sir,
certainly.
thank you very much, Professor Abhilash. Thanks, and everyone from your teams. Thank you, sir.
Thank you so much.
Thank you so much.